This is the first of the BocaPhysics mini course on nuclear physics. Over the next few lectures, we'll be talking about the composition of nuclei, their size and shape. We'll be discussing binding energy. We'll also get into the exponential decay law, and that has to do with half-lives and rates of decay. We'll also do an example on radiocarbon dating. We'll talk about alpha, beta, and gamma radiation, and that lecture will focus more on how those processes occur. I'm going to leave the discussion, more rigorous discussion of alpha decay to its own separate lectures because we have to get into quantum mechanics in a little bit more detail. Nuclear reactions we'll get into, and also fission and fusion. But before we begin with today's lecture, which is going to focus on composition of nuclei and the size and shape and binding energy, I want to sketch out the experiment that led to the discovery of the positively charged nucleus. And the two assistants of Rutherford, Geiger, and Marsden had an apparatus that looked like this. You had an alpha source. So yes, these are the same alpha particles as we'll talk about in alpha radiation. Basically, alpha particles are just twice ionized helium atoms, or helium for nuclei. Anyway, there's an actual source of alpha particles, and they place them behind a shield, and there's a small gap in the shield. And those particles struck a thin foil. What they observed was that most of those particles, alpha particles, passed through the foil undeflected, or deflected to a very small extent. A few of them, however, were deflected at wild angles. So that is what led Rutherford to the conclusion that there must be positively charged nuclei in atoms. And I don't imply that they're all going out at the same angle, but very big angles as opposed to being deflected to just a small extent. So, nuclei contain, are positively charged. And I'm getting a little bit ahead of myself here, but the first nuclear reaction that was ever observed again led Rutherford to the conclusion that there were hydrogen nuclei, or hydrogen nucleus, inside of every nucleus of every species. And he called that hydrogen nucleus the proton. And proton comes from the Greek word for first one. A little bit later, the English physicist Chadwick discovered the existence of the neutron, which carries no net charge. So nuclei contain protons and neutrons, but what about electrons? Is that possible? And the answer is no. And I'll in fact get to that question a little bit later in today's lecture, why electrons can't be inside of nuclei. So let's get started with composition of nuclei first off, and talk about some definitions. Nuclei are positively charged. They contain protons and neutrons, with the exception, of course, of one of the species of hydrogen, which just has a single proton in its nucleus. Another important factoid that we'll be getting into in a lot more detail in upcoming lectures is that radioactivity originates inside of the nucleus. So let's get to the definitions. We'll begin with atomic number. Atomic number is the number of protons in an element, so that's represented by the capital letter Z. Capital N represents neutron number, number of neutrons. Capital A represents mass number, and that's the total number of nucleons. The word nucleon refers either to a proton or a neutron. And therefore mass number is just equal to Z plus N, or number of protons plus number of neutrons. I want to go over next some of the features of protons versus neutrons. mass of the proton and neutron is almost the same. Mass of the protons, 1.673 times 10 to the minus 27 kilograms. The mass of the neutron is a little bit larger at 1.675 times 10 to the minus 27 kilograms. And the mass of the electron is much smaller at 9.11 times 10 to the minus 31st kilograms. So mass of proton and mass of neutron, both of those are roughly 2,000 times larger than the mass of the electron. Now, protons carry positive charge. Neutrons carry no net charge, and electrons, of course, carry negative charge. And the charge that protons carry is equal and opposite in sign to the charge carried by electrons. Now, another thing about protons and neutrons is that they're not fundamental particles. And what I mean by that is that they actually have internal structure. They're composed of smaller particles, and those particles are called quarks. So a proton, neutron, both of those are composed of 3 quarks, but that's getting into particle physics, so I'm going to just leave it at that comment. Electrons really are fundamental particles. And another important point about protons and neutrons, well, protons are stable outside of the nucleus. Neutrons are not. And what that means, if a neutron's not stable, is that it will decay into something else. It will undergo radioactive decay. And in fact, one of the products of that decay will be the proton and a couple of other particles. And in fact, I will get into a discussion of the decay of a neutron when we talk about beta decay. Okay? And by the way, electrons are stable also as well. Okay, so that's the mass, charge, and a little bit of the internal characteristics of protons and neutrons, and also the stability. So what I want to get to next is what symbol to use to represent a nucleus. So the way you write this is that you have an X, which represents the element, and the A, of course, represents the mass number. Some people go a step further, and they will actually add in a capital Z to represent the atomic number. That's not really necessary, because once you know what X is, once you know what the element is, you automatically know what the number of how many protons it has. So that's one way of writing it. Another way is to actually make all 3 of those quantities explicit. So you've got your element, you've got the mass number, you've got the atomic number, and you've got the neutron number as well. A nuclide is a species where both the number of protons and number of neutrons are specified. I'm sure everyone is familiar with the term isotope. But I'll define it here again anyway. Isotope means that you have species with the same number of protons. Okay, so let's consider the isotopes of hydrogen. And before I get to that, let me just write down the symbols for hydrogen 1. That would just be one superscript. That means it has mass number 1 proton. So another way of writing this would be H with a 1 superscript and a subscript 1 on the left-hand side. Or you could write this as H110. So we've added a 0 subscript on the right-hand side to represent the number of neutrons. So for hydrogen 1, that only contains, the nucleus only contains a single proton, no neutrons. So let's look at the isotopes of hydrogen. We got hydrogen 1. Its isotopes, commonly known ones are hydrogen 2 and hydrogen 3. Hydrogen 2 is actually called deuterium, and hydrogen 3 is called tritium. So those are the isotopes of hydrogen 1. They have the same chemical symbol, same elemental symbol, but they have a different number of neutrons, okay? The term isobar refers to species with the same mass number. So let's take oxygen 16. That has 8 protons and 8 neutrons. An isobar of that would be nitrogen 16. But that only has 7 protons and has 9 neutrons. So oxygen 16, nitrogen 16 are isobars of each other. So that term might be a little less familiar. Isotope refers to species with the same neutron number. So let's take gold 197. And mercury 198. So they have different mass numbers, obviously different elements here, so different numbers of protons, but they have the same neutron number. So that's what an isotone is. Okay. Now, when I first wrote down the masses of proton, neutron, and electron, I wrote those in terms of the kilogram. Now, that's not a convenient unit to use when we're talking about nuclear species. Far more convenient unit to use is the atomic mass unit. And that's written as lowercase u. And it's defined to be exactly 1/12 of the carbon-12 atom. So writing your mass of proton, neutron, electron in terms atomic mass units. That'll be 1.007276 atomic mass units for the mass of the proton. .008665 atomic mass units for the mass of the neutron, and finally for the mass of the electron, that's going to be 0.000548 atomic mass units. Okay? So mass of proton, mass of neutron, very nearly equal to 1 atomic mass unit. Let's go ahead and look at a table of nuclear data next. This is a sample of a typical table of nuclear data. The element, mass number, atomic mass, half-life, abundance or level width, quantum number for total angular momentum of the nucleus, and decay mode are given. Consider the first two entries, hydrogen 1 and hydrogen 2 or deuterium. Both of these nuclides are stable, so their abundances are listed. Hydrogen 3 or tritium is not stable, and its half-life of 12.32 years is given, and the decay mode of beta minus. Notice for uranium-231, the half-life is 4.2 days, but two decay modes are listed, electron capture and alpha decay. Oftentimes, authors will leave off decay modes that occur with small probability. So U-231 most likely occurs with electron capture, although alpha decay is possible. Further note that for some species that are extremely short-lived, that the level width is given instead of a half-life. And moreover, for extremely long-lived species, not only is a half-life given, but the abundance is given as well. We'll discuss decay modes in the lecture on alpha, beta, and gamma radiation. This is a Segre chart, which shows proton number and neutron number of nearly all of the more than 3,300 known nuclides. Of all known nuclides, only a few hundred are stable, and these are represented by black squares. Colored squares give an indication of the order of magnitude of the half-lives of unstable nuclides. The term half-life means the time it takes half the sample to decay. Half-lives will be discussed in detail in the exponential decay law lecture. White squares represent the longest lived species, with half-lives on the order of 10 to the 15th years, 10 to the 21st years, and so on. Beige squares represent species with half-lives on the order of 1 billion years. Uranium-235 has a half-life of 704 million years, and uranium-238 has a half-life of 4.47 billion years. So half-lives range from 10 to the 21st years and more, down to the tiniest fraction of a second. Radioactivity originates in the nucleus. Unstable nuclides undergo radioactive decay, and stable nuclides do not. In the lecture on alpha, beta, and gamma radiation, we discuss how these three decay processes occur. Finally, note that the valley of stability lies pretty much along the Z equals N line for lighter nuclides, but veers towards the neutron-rich region as the number of nucleons increases. The heaviest known nuclide is bismuth-209, and I state that with a caveat. The caveat being that some species that were believed to be stable actually were radioactive with extremely long half-lives. And the reason for the change of status is improved experimental technique. Now let's turn our attention to the questions, how big are nuclei and what shape are they? Well, it was Rutherford, once again, who ascertained that nuclei have the radii on the orders of a few femtometers. And 1 femtometer is equal to 10 to the minus 15th meters. Contrast that with the size of an atom. Atomic radii are on the order of angstroms, or on the order of 10 to the minus 10 meters. So as it turns out, the radius of most nuclei is well approximated by this expression. So R naught is a constant. And A, once again, is mass number or the number of nucleons. Depending which source you consult, people will oftentimes use different values for R naught. Some people will use a value of 1.5 femtometers. That's, of course, determined experimentally. Sometimes they'll incorporate a quantum correction, basically from the shell model. So that's 1.2 femtometers. And then some people will use the value 1.07 femtometers, and that is basically the mean electromagnetic radius, and I'll get to what I mean by that expression in a minute. So let's just calculate the radii of a couple of common species. Let's say oxygen 16. So that has a radius equal to 2.7 femtometers. And the radius for uranium 235 is equal to 6.6 femtometers. Okay, so I guess from one standpoint it makes sense that the more nucleons that are in a nucleus, the larger the radius. But notice another aspect of this. What this means is, or what you should glean from this expression, is that the density of nuclei is the same across species. Density is equal to mass over volume. And I can write the mass of a nucleus in terms of its mass number times U. You see, it's a decent approximation because the mass of most nuclei, to a rough degree, is equal to the mass number times U. And maybe you should use a squiggly line here instead. Okay, and the volume is equal to 4 pi over 3 r cubed. But r is equal to r naught times 8 1/3. So you see what happens here. This a cancels with the 1 in the denominator. So as it turns out, there is no dependence on the number of nucleons, and therefore the density is about equal to 10 to the 17th kilograms per cubic meter. And by the way, for U, I just plug in the value 1 atomic mass unit is equal to 1.66 times 10 to the minus 27th kilograms. So that gives me a density of 3 times 10 to the 17th kilograms per cubic meter. Now compare that with the density of ordinary liquids and solids. Water, for instance, just has a density of 1,000 kilograms per cubic meter. So this means that the density of the nucleus is something like 10 to the 14th times greater than the density of just ordinary matter. Okay? And I don't mean to imply either that you have a density profile that looks like this. This is a radius, and you have some about 3 times 10 to the 17th kilograms per cubic meter, and it's constant and abruptly drops to 0. No, the density profile actually looks like this. And this is the mean electromagnetic radius. It's where the density drops to half of its value. So this is what the value that we're using for R naught in our calculations, which is a 1.07 femtometers. Okay? So That's how big they are, that's the density. Well, what shape are they? Well, most nuclei are spherically shaped. Some of them, however, are kind of like prolate spheroids or oblate spheroids. So prolate spheroid is like something that's stretched out a little bit. Oblate spheroid is a sphere that's kind of been squished down a little bit. Okay? Okay, so those, it's convenient to use atomic mass units for the mass, femtometers for the radius, and as it turns out, we need to use a different unit of energy from the MKS unit of the joule, because in fact that is much too large for any calculations that we'll be doing. As it turns out, the electron volt, and specifically the mega electron volt, when we talk about nuclear physics, is far more convenient. So 1 electron volt is equal to 1.602 times 10 to the minus 19th joules. In nuclear physics, we want to use the mega electron volt, and that's equal to 1.602 times 10 to the minus 13th joules. Now, definition of the electron volt is that that is the amount of work that's needed to take an electron through 1 volt. So we'll be using working in units of mega electron volts. Now there's a convenient conversion, and with that conversion, I'm going to go back to probably the most famous physics equation of all equals mc squared. This embodies the principle of equivalence between energy and mass. So this is the rest energy of a certain something of mass n. Okay? So I'm going to go ahead and calculate the energy of something that has mass of 1 atomic mass unit. And once again, I'm running out of space, but I'll just write it down below here. 1.66 times 10 to the minus 27 kilograms times 3 times 10 to the 8th meters per second, all squared. And then I'm going to multiply by a conversion factor. To convert from joules to mega electron volts, and being a little careless with the number of significant digits here, but anyway, the upshot of it is that it's going to be equal to 931.5 mega electron volts. So this gives me a nice little conversion here. Basically, 1 atomic mass unit is equal to 931.5 mega electron volts over c squared. So a lot of times you'll see mass expressed in, instead of atomic mass units, in mega electron volts over c squared. So therefore, these masses can also be written as 938.3 mega electron volts over c squared. Neutron is 939.6 mega electron volts over c squared. And finally, the mass of an electron is equal to 0.511 mega electron volts over c squared. Okay? So if you've got nuclei, in the case of uranium-235, that has 92 protons, and those protons do experience electrostatic repulsion. So the question is, how in the world do nuclei, U-235 or any nucleus, how does it stay intact? How does it stay together? Before the advent of modern physics, there really were 2 fundamental forces. You had electrostatic and you had gravitational. So let's see if gravitational force can possibly be the agent responsible for keeping nuclei intact. the gravitational force of attraction between two protons and electrostatic repulsion between those two protons. And let's compare the magnitudes. So force gravitational over electrostatic force. And it should be squared up there. Distance squared cancels out. Gravitational constant 6.67 times 10 to the minus 11. Mass of the proton is 1.67 times 10 to the minus 27 squared. And this constant K, and that's equal to 9 times 10 to the 9th. And the charge is 1.602 times 10 to the minus 19th. You're going to wind up with a value that's roughly in the order of 10 to the minus 36. So that tells you that the gravitational force is 10 to the minus 36, the magnitude of the electrostatic force. So there's no way the gravitational force could be the agent responsible. So as it turns out, there are actually two new forces, fundamental forces, that come up in modern physics. Gravitational is the weakest. And it turns out electrostatic is the second strongest. It's now the strong force that is the agent responsible for keeping nuclei intact, so-called strong force, because it's the strongest of the four fundamental forces. And there's also the weak force as well, but we don't get into it in nuclear physics. That's really getting into particle physics, okay? So let's look at what the features of the strong force have to be. These are the features of the strong force. First of all, it has to be very short-ranged. And the best or simplest evidence for that comes from experiments where proton beams are scattered by nuclei. It also has to be stronger than the electrostatic force. Why? Well, if it weren't stronger, then the protons inside of the nuclei would repel each other and the nucleus wouldn't stay intact. So it's stronger. It acts on protons and neutrons equally, and it also doesn't depend on electric charge. And the best evidence for that comes from collision experiments where protons collide with protons, neutrons collide with neutrons, protons collide with neutrons. And finally, it doesn't affect electrons. And the best evidence for that comes from high energy electrons collide with nuclei. Okay? So those are the general characteristics of the strong force, but I'd like to make the strong force a little bit more concrete. So to do that, I'm going to treat a nucleon in a nucleus like a particle in a box. And the particle in the box is a very famous problem from quantum mechanics. And essentially, such a particle has to have some minimum kinetic energy. I'm just going to quote you the result here. This is equal to 3 h bar squared pi squared over 2 ma squared. H bar is equal to h over 2 pi. H is Planck's constant. M is the mass of the particle, in this case the nucleon, and A is the size of the box, or the edge length of the box. I'm going to multiply and divide by c squared. Make my calculation a little easier to handle so I'm not goofing around with a bunch of crazy units. H bar c is in fact equal to just 200 mega electron volts femtometers squared times pi squared. Talking about a nucleon, so nucleons have energy equal to 940, or rest energy equal to 940 mega electron volts. And finally, the edge length. Well, what nucleus are we talking about? Well, why don't we use one of the two nuclei that we already did a calculation on. If you recall, we calculated the radius of oxygen 16, and that has a radius equal to 2.7 femtometers, and that's using the mean electromagnetic radius for that. And for the edge length will be 5.4 femtometers squared. Now when I do the math, I want to end up with a value that's on the order of 22 mega electron volts. So what it tells me is that any nucleon inside of an oxygen 16 nucleus has to have minimum energy 22 mega electron volts. So therefore, the potential energy well, due to the strong force, has to be greater than this. I mean, the total energy has to be negative, otherwise this particle would not be bound. Well, your potential energy is going to look something like this. Well, it falls off to 0. There's the well here, and it's about 1 femtometer. This is around 2 femtometers. And I don't know, let's say this is minus 100 mega electron volts. Okay? So it goes to 0. Very fast. Strong force goes to 0, so therefore the edge of the well is roughly 2 femtometers. Has to be bigger. The depth of the well has to be bigger than the kinetic energy. And ultimately, although the strong force is attractive, it's going to have to become strongly repulsive as nucleons get closer and closer together. And why so? Well, you can understand it from this bit of reasoning. If it were purely attractive, then everything would just be drawn together. So once it gets too close, the strong force actually becomes repulsive. And that is basically the general characteristics of the strong force and the potential energy due to the strong force. Okay? Now, at the beginning of this talk, I mentioned or posed a question, are electrons inside of nuclei? Is that possible? So I'm going to get to that question next. Nuclei are composed of protons and neutrons. But let's suppose for the sake of argument, nuclei were composed of electrons and protons instead. I'm going to show you 2 arguments why that can't be the case. And the first argument is going to have to do with the energetics of this system. So let's suppose that we've got the Z protons inside the nucleus, but instead of having neutrons, you've got an additional A minus D protons. So basically you'd have N, capital letter N protons. The hypothetical mass, or the mass of this hypothetical system would be roughly the same as the actual system, which is composed of protons and neutrons. Remember, protons and neutrons have masses very close to each other. We also have to have A minus C electrons, and that will cancel out the charge due to those additional A minus C protons. So to look at the energetics of the system, I'm going to treat the electron in the nucleus like a particle in the box. So would it seem to be that we could use that same expression that we did did last time around, 3h bar squared pi squared over 2ma squared to calculate the minimum kinetic energy that such an electron would have. However, there's a problem, and the problem with just using this expression is that the electron has such a small mass that relativistic effects become important. So I've got to go down a little bit different route. And I'm going to make use of what's the so-called Pythagorean relation, and that's E is equal to square root of P C quantity squared plus MC squared squared. This is the contribution from the rest mass, and this is the momentum term. So how do you calculate the momentum term? Well, we are treating like this is a particle in the box. And we'll assume that our box is cubical. This P squared, magnitude of the momentum squared is just equal to the sum of the squares of each of its components, px, py, pz. Px is equal to h over 2a. Again, a, remember, is the side of the box, the length of the side of the box. Okay, so because each of these directions is the same, let's just basically multiply this 3 times h over 2a quantity squared. Pc squared then is going to be three times hc over 2a all squared. Now I'm going to go ahead and assume that the nucleus in question is an oxygen 16 nucleus. And we calculated what the radius of that nucleus was, is about 2.7 femtometers. So therefore the edge length of our hypothetical box here is going to be equal to 5.4 femtometers. And this is just a convenient number to have in mind rather than throwing an extra calculation in there. HC is equal to 1240 mega electron volts femtometers, and this will be 2 over 5.4 femtometers. That's roughly equal to 40,000 mega electron volts squared. Okay, what's the rest mass, or rest energy rather, of the electron? Well, I just had it written up in the board just a few minutes ago, but anyway, that's equal to 0.511 mega electron volts. Okay, so clearly if I do the math here, this term is so much smaller than this PC term. It's actually PC is about equal to 200 mega electron volts. So therefore the energy is just equal to 200 mega electron volts. And likewise, the kinetic energy of electron, which is equal to E minus mc squared. And once again, because the mass of the electron is so small, its rest energy is so small in comparison. So it's still going to be roughly 200 mega electron volts. Again, we're just looking for a ballpark figure here. That's why I'm not being all that careful with significant digits. Okay, so that's the kinetic energy that such an electron would have, and it's much, much larger than the kinetic energy that we calculated for a nucleon in a similar nucleus. Well, assuming that, since we're assuming that there are only protons and electrons, and we're forgetting about this strong force, it's interesting if you ask the question, well, how much potential energy is available to confine this particle? Well, from electrostatics, the electrostatic potential is equal to K, K is a constant, times charge Q over 2 big R. Big R represents the radius of the spherical charge distribution, and this is times 3 minus little r squared over big R squared. Little r represents the point of observation. Now, our goal here is to figure out what the potential energy is of an electron at the center of a spherical charge distribution. So it's going to be minus E times its electrostatic potential evaluated at the center. Okay, now the charge Q that the electron sees is going to be actually Z plus 1 times E, not just Z. And the reason for that is because we're moving one of those electrons into the center. We're treating it and looking at that particular electron and the effect on that due to all the other electrons and protons in it. So this is why this is going to be Z plus 1. So we've got actually 2 E's in the numerator then over 2R, and yes, I'll leave off the factor of 3 out front. I'm going to write it up a little higher here. And that's going to be equal to minus 7.2 mega electron volts. Okay, so let me just read this off. This is 3 times 9 times 10 to the 9th, that's at constant K, times 9, that's Z plus 1. The net charge on this oxygen 16 nucleus is ZE, but remember, because we are pulling one of those electrons into the center, and we're looking at the energy, potential energy experienced by that one electron, that's why it's going to be Z plus 1, not Z. Times 1.602 times 10 to the minus 19th, and all over 2 times 2.7 times 10 to the minus 15th. 2.7 times 10 to the minus 15th is the radius of our spherical charge distribution, the nucleus essentially, and I want to express this in units of electron volts. So do the math here. It's actually minus 7.2 mega electron volts. You can compare this value with the rough estimate of the kinetic energy of the electron. You see that there's nowhere near enough energy to confine this electron inside of the nucleus. So that is a very good argument against there not being any electrons inside of nuclei. Okay? Now I mentioned that there were several arguments that I was going to present. The second one has to do with the magnetic moment. Now the Bohr magneton has value EH bar over 2 times mass of the electron. There's also a nuclear magneton that has value EH bar over 2 times mass of the nucleon. Mass of the electron is so much smaller, rough estimate, it's roughly 1/2000th the size of the mass of either a proton or neutron. So therefore, this term would dominate. Now, when the magnetic moments are measured, you would expect that because this Bohr magneton is so much larger, that if there were electrons inside the nucleus, that's the value that would be measured. Yet, it's actually values that are more on the order of the nuclear magneton. Okay, so that's another argument against there being electrons inside of nuclei. One other point I want to make too, protons are positively charged, so therefore it doesn't seem strange that they'd have a magnetic moment. Neutrons, however, don't carry any net charge, and yet they do still have magnetic moment. And the reason for that is that, remember earlier I said that both protons and neutrons are not fundamental particles. They're actually composed of smaller particles called quarks. And those quarks do carry charge. So that's the reason that you'll see there'll be a nuclear magneton associated with neutrons as well as protons. Okay, but I digress. Anyway, two important points as far as this lecture is concerned. From energetic arguments, you can see that there are going to be electrons inside a nuclei, and also looking at the magnetic moments, that's another argument against there being electrons in nuclei. And that, in addition to all the copious experimental evidence out there. And there's also a question of the spin, too, but we're not going to get into that in this lecture. Anyway, the last topic that we're going to get into today has to do with binding energies, so let's get to that next. It's a relativistic effect that the mass of a balanced system is smaller than the sum of the masses of its constituent parts. So, pre-relativity, you might have thought that the mass of the atom was simply equal to the mass of the nucleus plus Z times mass of the electrons. This is not so. There's actually a binding energy which is equal to mass of the nucleus plus Z times mass of the electron minus mass of the atom times C squared. Now, as it turns out, this quantity is not going to be important in our calculations. Let me move on to the nucleus. The nucleus is composed of Z protons and N neutrons. So again, you might have thought, pre-relativity, mass of the nucleus was simply equal to Z times mass of the protons plus N times mass of the neutrons. Again, not so. There is a binding energy associated with separating out all the parts. So binding energy is equal to Z times mass of proton plus N times mass of neutron minus mass of the nucleus times C squared. This, again, is a binding energy. And that's the energy required to separate all the nucleons. Okay. Now, because the data in nuclear tables is the atomic masses are given rather than nuclear masses, I'm going to rewrite this expression. I am going to add Z times mass of the electron and subtract it off. So this first term, mass of proton plus electron, well, that's just the mass of hydrogen. So this is Z times mass of hydrogen. By the way, this binding energy associated with the electrons is only on the order of kiloelectron volts, and nuclear binding energy is actually an order of mega electron volts. So in many cases, we can ignore this effect entirely, and we will be ignoring it in this class. So this is why I can rewrite this expression as Z times mass times hydrogen plus number of neutrons times mass of a neutron minus mass of the atom in question. I'm going to calculate the binding energy for a couple of systems. Hydrogen just has one proton, so there is no binding energy associated with the nucleus, or I should say there is no nuclear binding energy. But let's look at a deuteron, or what is the same thing? Hydrogen 2. What is the binding energy of that nucleus? Well, this is equal to 1, because there's only one proton, one neutron, times mass of hydrogen, which is 1.007825 atomic mass units, plus 1 neutron, times mass of neutron, which is 1.008665 atomic mass units, minus mass of the hydrogen 2 atom, which is 2.014102 atomic mass units, and I'm going to multiply by c squared. Multiplied by a conversion factor. Same conversion factor we worked out just a little bit ago. It's 931.5 mega electron volts over c squared is equal to 1 atomic mass unit. So this c squared will cancel with this one, and this u in the denominator will cancel with all those other u's. And we'll wind up with 2.22 mega electron volts. Now, it's very useful, too, to calculate the binding energy per nucleon. And the number of nucleons in this case is just 2, so the binding energy per nucleon for hydrogen 2 is just 1.1 mega electron volt per nucleon. Now, what about heavier nuclide? Let's say uranium-235. Let's calculate the binding energy for this species. Let me read this off. This is 92, the number of protons, times 1.007825 atomic mass units, that's the mass of hydrogen, plus 143 times 1.008665 atomic mass units, again, that's the mass of a neutron, minus 235.043930 atomic mass units. That's the value, of course, from the nuclear data tables, and that's times c squared. That gives me the binding energy. Now, I want to express that in units of the mega electron volts, so I multiply by the conversion factor. And when I do the math, I will wind up with $1,784 megaelectron volts. And once again, I'm going to go ahead and calculate the binding energy per nucleon. Which is roughly 7.6 megaelectron volts per nucleon. So is there some kind of a trend regarding binding energy per nucleon across species? Let's go ahead and take a look at a plot of the binding energy per nucleon for just about every known nuclide. The binding energy per nucleon for nearly every known nuclide is plotted in this figure. The binding energies were calculated using atomic masses from a nuclear data table. Hydrogen-1 is excluded, of course, because its nucleus is composed of a single proton and has no binding energy. Notice that the binding energy per nucleon climbs steeply as mass number increases for light nuclei, but then levels off. The binding energy per nucleon for most nuclei lies between 7.5 megaelectron volts and 8.8 megaelectron volts. To get insight into the binding energy, let's take a look at the Weizsäcker semi-empirical formula. Binding energy can be written as some constant times A, of course, is just the mass number or number of nucleons, minus some other term that is proportional to A to the 2/3, minus another term that's proportional to z squared over A to the 1/3, minus another term that is, looks like it's proportional to the difference between the number of protons and neutrons divided by A, and then finally a term that goes over A to the 1/2. So I want to break this down term by term. This formula, or these constants out front, were determined by fitting this expression to experimentally measured data. Now, why is that called a volume term? Well, volume is just 4 pi r cubed over 3, and if we plug in that expression, r naught A to the 1/3, and I cube that, that tells me this term is proportional to A. And essentially what this is saying here is that the binding energy is linearly proportional to the number of nucleons, with a bunch of corrections to that. Remember, the nucleons are bound by the strong force. The strong force is very short range. So the nucleons are bound to its nearest neighbors, or a nucleon is bound to its nearest neighbors. Now the second term goes as A to the 2/3, and to understand that, to calculate the surface area of the sphere, it's just equal to 4 pi r squared, and again, plugging that r naught A to the 1/3, that term is proportional to A to the 2/3, and this is why I call this surface constant. Now, this third term is Coulombic in nature, and the potential energy is proportional to z squared over r. And once again, if I make use of the fact that r can be written as a constant, r naught times A to the 1/3, I see that this is proportional to z squared over A to the 1/3. Okay? So let me just go over this again. The first term tells me that the binding energy is linearly proportional to the number of nucleons, and nucleons are bound to their nearest neighbors. It's very short-ranged. Strong force is very short-ranged. However, the nucleons that are on the surface of the nucleus don't have as many nearest neighbors, so there's going to be a little correction to that. There's also going to be a correction because of the repulsion, electrostatic repulsion between the protons, and that contribution is going to be proportional to z squared over A to the 1/3. This fourth term is quantum mechanical in nature, and it's due to the symmetry effect And I'll get into that in a different lecture where we get into quantum mechanics in a little bit more detail. But anyway, what you can see is that as the number of nucleons increases, this contribution goes down, and furthermore, there will not be anything subtracted off if the number of protons and neutrons are equal to each other. The final term is basically an empirical correction to account for the fact that protons tend to pair with protons and neutrons tend to pair with neutrons. Epsilon takes a value of +1, 0, -1. It's +1 if both number of protons and neutrons are even, and it's 0 if one's even or the other's odd, and it's -1 if both Z and N are odd. And I wrote a couple of other terms up here, and that's because different authors will use fit this the data to slightly different formulas. So some people write this term as going as A over to the 4/3, and some will go as 1 over A. Okay? Well, let's wrap this up by looking at a plot of the binding energy per nucleon calculated using the semi-empirical formula. Now, I do want to emphasize that this formula does not work well for the lighter species. Excellent agreement, however, once you get into the heavier species. Here's a plot of binding energy per nucleon calculated from the semi-empirical binding energy formula. There is excellent agreement between the binding energy per nucleon calculated these two ways for A greater than 20. For smaller a, the semi-empirical binding energy formula fails. Species for which this formula yields an utterly nonsensical result were also excluded from this plot.